Hello everyone. So today we're going to talk about Cauchy's theorem and Cauchy's formula. Now, Cauchy's theorem is the following statement, and this is something I've mentioned in class before, but here's the careful statement and we'll go over the proof as well. So we're supposing that we have an analytic function, f of z, on a domain D, and you can refer to the figure that I've drawn here to get a sense of what I'm talking about. Gamma is a piecewise smooth, simple, closed curve, which is oriented counterclockwise. Okay, so you can see the picture of that in the figure, and we're going to be using this long list of adjectives for curves a bunch in this lecture. So I'll just call such a curve typical. So if I say a typical curve, I mean it's piecewise smooth, simple, closed, and oriented counterclockwise. Okay, so we have a typical curve in D, and we're supposing that the inside of omega, so the region that's bounded by our gamma, is contained in D. And additionally, this is important, we're assuming that f prime, so f is analytic, so it has a derivative, we're going to assume that that's continuous. Okay, and if we do that, then we can prove rather simply that the integral of f of z around gamma is equal to 0. Okay, and here's the proof of that, and it's really just Green's theorem. So here goes. Well, the integral around gamma of f of z dz, well, since gamma is piecewise smooth and bounds this region, we can apply Green's theorem, and not just that, we can apply Green's theorem because f prime is continuous. Okay, so we're going to apply complex Green's theorem here, which is really just real Green's theorem, two applications of real Green's theorem, as we've seen before. So this is 2I times the integral over omega of df dz bar dx dy. Right? And this is, so this equality, this is Green's theorem. And this is where we're using, so this uses that f prime is continuous. Okay, if f prime wasn't continuous, so what f prime being continuous means is that basically that the partial derivatives of the component, the real and the imaginary parts of f are continuous. Okay, and those partial derivatives show up in this df d by dz bar. So if those weren't continuous, we wouldn't necessarily be able to do this integral over omega. Okay, so that's where the continuity comes in. And, well, df dz bar equal to 0 is equivalent to the Cauchy-Riemann equation. So since f is analytic, we know that this integrand is dead equal to 0, right? The whole integrand, and then we're integrating 0, so we get 0. And this equality is the CRE's, Cauchy-Riemann equations. Okay, so rather simple theorem, but very, very interesting to note. Okay, so any old analytic function whatsoever, as long as we have f prime being continuous, we know that if we integrate that around a closed loop, that we're going to get 0 as the answer. Okay, so let me see if I can. You're going to have to bear with me as I deal with this technology here. So let me just move this to the side. Okay, so here's a little note. Eventually, we will remove the hypothesis f prime is continuous. So it's going to turn out that just knowing that the complex derivative exists automatically implies that the complex derivative is continuous. And that's the CREs. I mean, so complex derivative existing, we've seen is already seems like a pretty strong condition on the real and the imaginary parts. So it's going to turn out that if those real and imaginary parts satisfy the Cauchy-Riemann equations and our function f is real differentiable, so that is to say our function is complex differentiable, it's going to automatically turn out that f prime is continuous. Okay, but that will take some work, and actually that was something that not even Cauchy knew when he was developing this subject. So that took a while to kind of figure out that you could remove that assumption. It's definitely a very non-trivial thing. Okay, so for now we're going to use the following terminology because we're going to be using this hypothesis that f prime is continuous. So if we say that f is analytic on D, we're going to mean that f prime exists on D. But if we say that f is holomorphic on D, that's going to mean that f prime exists and f prime is continuous on D. Okay, so actually analytic and holomorphic, as I said, it's going to turn out they're exactly the same thing, but we don't know that yet for sure. So we want to just have a shortcut. So we'll just say f is holomorphic on D, and that'll mean both of these things. It's analytic and f prime is continuous. Okay, so the proof of Cauchy's theorem was so simple using Green's theorem that it's hard to resist the urge to prove other things that way. So here's something that we can prove that way, and this will be useful to us coming up. So the basic situation is that we have some domain. So let's say, so I'm going to draw us a picture here. So let's say we have some domain. Call this D. Yeah, let me. Okay, so this is going to be our domain D. And let's say we have. Let's say we have a typical curve. Okay. Oh, maybe our D. Let's say maybe D has a hole in it somewhere. Okay, so the point is going to be. Oh yeah, so D could have a hole in it there. It could also have a hole here. So let me illustrate that. Just try to be patient here while I'm using this technology to generate this picture. Okay, so D is here, and D is also going to be in here, but it's not in these holes. And yes, or that red curve there, that's we'll call that gamma 1, and let's have a blue curve, which we'll call this gamma 2 in blue here is going to also be a typical curve. Okay, so that is to say this is oriented counterclockwise like this. Okay, so in this picture here, if we have a function which is analytic on D, or sorry, excuse me, holomorphic on D, gotta be careful about that myself. So we have a function f which is holomorphic on D. It'll be easy for us to show that the integral around gamma 1 of f is the same as the integral around gamma 2 of f. Okay? And basically the reason is going to be because, well, we can we can look at the integral around gamma 1 minus the integral around gamma 2. And using Green's theorem, that will be equivalent to an integral over this region that's in between gamma 1 and gamma 2. But we know that our function is holomorphic in that region in between. It satisfies the Cauchy-Riemann equation. So that integral, that double integral, is going to vanish for the same reason that it did in the previous proof. Okay, so that's essentially the proof. So let me state that here. Let me see if I have another color. Yeah. So I'm going to want to look at this yellow region in between. That's going to be the region that we're integrating over. Black. Here we go. Okay, so here's a proposition. So here's the theorem. We'll find this useful as well. And I should note that I'm kind of not strictly following the development in the book step by step. In broad strokes I am, but I'm kind of walking you through the material in my own idiosyncratic way. And the book doesn't have this sort of principle singled out, I don't think. It certainly doesn't call it this, but so here's a theorem. So this is going to be referred to as the weak homotopy principle. So this is WHP. I'll probably just use that abbreviation. And what it says is just a translation of what I was saying before. So let gamma 1 be a typical curve. Let's say with interior omega 1. Okay, and let's see, so gamma 2 be a typical curve in omega 1 with interior omega 2. Okay, and then we're going to suppose that F is holomorphic on a domain that contains the part in between those two omegas. So suppose F of Z is holomorphic on a domain T containing, let's see, so let's say it contains the closure of the region omega, which is the region between the two curves. So omega is gamma, let's see, so gamma 1 minus omega 2 closure. Okay, so omega is this open region in yellow between the curves gamma 1 and gamma 2, and then our domain D contains the closure of that region. So that would be that open yellow region there, and the curves gamma 1 and gamma 2. So that's all I'm trying to say there. So let's see, maybe I should indicate that omega is in yellow in here. Okay, then the integral over gamma 1 of f of z dz is equal to the integral over gamma 2 of f of z dz. Okay, so here's the proof, very simple. Let's just start with the since I already sort of explained the idea of the proof is to use Green's theorem, let's start with the integral over, so double integral over omega of df by dz bar, right? So we know our f is holomorphic, so df by dz bar is 0, so the integral of that is 0. And, well, by Green's theorem, this is the integral over the boundary of omega, and that's gamma 1 minus gamma 2, right, of f of z dz. And so this is equal to the integral over gamma 1 of f of z dz minus the integral over gamma 2 of f of z dz. Okay, and then rearranging that equation immediately implies the theorem. All right. So this is called the, maybe I should just remark on the name, this is called the weak homotopy principle. The homotopy part comes from the fact that, well, it's pretty intuitive from the picture that this curve gamma 1, right, you can see, you can think about you're looking at the integral of f over gamma 1, that's your starting curve. It seems reasonable from the picture to conclude that you can deform gamma 1 continuously into the curve gamma 2. Now you can sort of just, you could like mush this curve gamma 1. I'm kind of out of colors here, so I don't know how to, maybe I can just use the black. Yes, you can kind of imagine mushing this curve, the red curve, continuously into the blue curve. And so basically this principle says that this hypothetical mushing you do of the curve, that doesn't affect the value of the integral. So the new curve you get after you continuously mush the red one is the same as the integral over the blue curve at the end. And there's a much stronger version of this which is true, which maybe we'll get around to later. So this one is, that's why I called it the weak homotopy principle. And that's because we have these assumptions on the curve. The curves are typical, so they're not intersecting, self-intersecting. They're not intersecting each other. The region omega between them is particularly nice. But there's a much stronger version of this principle, which is true, which basically broadly says that as long as you can deform one curve to another continuously in some very technical sense, a very, very technically specific sense, then that's not going to, the value of the integral is not going to be affected if your function is holomorphic. But we'll be satisfied with this version for right now. We can go pretty far with just this. Okay. So, move on from this. Let me see here. Where did my, oh, there it is. Just keep all that stuff together if we can, in case I need it. Okay. So now we're going to talk about Cauchy's formula. Okay, so here's the situation. Let's say we have a typical curve. Yeah, maybe I should do it. Maybe I should do it in red. Stick to the same thing I was doing before. So let's say we have a typical curve in red here. That's gamma. And let's say we have a function whose domain contains this gamma in the inside. So the domain be encircling this like that, and maybe there's a hole in the domain. Okay, and so let's take a point Z inside of here. And so this is what I'm doing here is I'm going to try to motivate Cauchy's formula, sort of how Cauchy might have discovered this formula. So back in the day in calculus, sort of working with power series was pretty common. Like Newton was a fan of power series, and so is Euler. So it's not inconceivable that Cauchy might have been sort of thinking this way. So basically what we have is, so we're going to pretend we have an analytic function, or let's say holomorphic function f, and we're looking at a point Z, and let's suppose that f of z can be expanded in a power series near z. So say in the disk around z of radius delta. Okay, so let's say that this disk here has radius delta. Okay, so if that's the case, then we'd have something like that. So let's say zeta denotes a point, or points. It's a variable denoting the points in this disk. Okay, so what would that mean? That would mean that f of zeta, and as zeta moves around in that disk, that's equal to f of z plus f prime of z times zeta minus z plus f double prime of z over 2 times zeta minus z squared plus ... Right? Okay. So what Cauchy, well, potentially this is the way you sort of figure this out, is that if we divide both sides of this by zeta minus z, right? So if we divide by zeta minus z, what Cauchy notices is that all this stuff here, well, that each of these terms, so this is just a constant, this is a degree 1 polynomial, and each of the remaining terms are higher degree polynomials. So, well, in particular, each of those things in that summand is a holomorphic function, right? So, by Cauchy's theorem, if we were to integrate each one of these individually around gamma, around our red curve over here, we would get 0 by his theorem, right? So, if we suppose, and this would be something that we in modern times would realize we have to justify, but back then people tended to freely sort of integrate these infinite expressions term by term. So if we integrate this expression in these brackets, then around gamma, then that whole thing should vanish, right? So you just sort of integrate this infinite sum. That should be the infinite sum of each of the integrals, and each of those integrals is 0. So basically we end up with a computation like this, hypothetically. So this should be, well, we would expect this to be somewhat justifiable, that the integral around gamma of f of zeta over zeta minus z d zeta. Well, first of all, okay, so I sort of want to integrate the power series on the right hand side, and so I want to bring that curve gamma in closer into the disk. So I can say that by the homotopy principle, the weak homotopy principle, this is equal to the integral on the boundary of this disk of the same thing, f of zeta over zeta minus z d zeta. And then that's equal to, let me see, oh no, sorry. And then that should be equal to the integral over the boundary of the disk of f of z over zeta minus z plus the integral over the boundary of the disk, and that's d zeta. And then plus all of the stuff in the brackets, right, d zeta. And this should be equal to 0. Right, because we know that stuff is, these are all holomorphic functions, so this power series expansion is valid in this disk, so we should be able to integrate over the boundary of that disk, that closed curve, and by Cauchy's theorem get 0. So this should be by Cauchy's theorem. And again, technically we would have to say the integral of this infinite sum is the infinite sum of all of the integrals to really be rigorous about that. But we're just kind of doing an exploration here, an exploratory calculation. And so looking at this term here, well, we're integrating d zeta, and f of z, that doesn't depend on zeta. Z is just this fixed point. So what we can say is that this is just f of z. And so pull that constant out in front, and then we have this integral around this circle of zeta minus z with respect to zeta. But you may remember we've done that integral before. It just comes out to be 2 pi I. Okay, so what we find is that f of z is equal to 1 over 2 pi I times the integral over gamma of f of zeta over zeta minus z d zeta. Okay. And notice, so let me see, let me go back to my picture over here, and let me call this region in here omega. Yeah, so all this is omega. So this z was just arbitrarily chosen in omega. So this formula, well, assuming that so remember we assumed that we could expand f into a power series near z, and we assumed that we could do this term by term integration. So we haven't justified that yet, but it seems likely to be the case that if we have an analytic or a holomorphic function, that it's going to be the case that for all z in omega, we can evaluate f of z by doing this integral around gamma, right? So we've cordoned off this region omega with this curve gamma. For every point inside of gamma there, we can compute the value of f just by computing this integral around the curve. So in other words, the value of our function, the values that our function takes inside this curve gamma, depend only on the values of f on the boundary curve gamma. So the values of f on the boundary completely determine the values of the function inside that region omega. And so somehow the boundary knows about, so if you know the function on the boundary, then the function's completely determined on the inside. Right? So once you've specified f on this relatively thin subset, just this typical curve, then you know the value. You have, if your function's holomorphic, you have to know the value everywhere inside of omega. So that's somewhat startling, and also the form of this integral. It's not a very complicated integral, really, because this f of z, so this z here, right, only shows up here, right? So really, you're integrating the input z only occurs in this simple rational function in the integral, in the integrand, and then you integrate that around the curve. So you have this relatively simple rational function of z. So it's really quite amazing. Okay. All right, so I didn't actually prove this theorem, just to reiterate again. This is kind of how you might wonder how this... Okay, so basically this is going to be the statement of the theorem that we have, and this is going to hold for all holomorphic functions in this situation here. So, but that's not what we proved here. So I assumed initially that you could expand in a power series, and then it sort of becomes, maybe more intuitive where this result comes from, right, by assuming that you have this power series expansion. But it turns out that once you figure out what the result should be, that you can actually justify it rather simply. Okay, so we made some unwarranted assumptions to arrive at the form of the result, but now we'll actually be able to prove the result. So let me hold on a second. Why isn't this eraser working? This is annoying. Okay, I want to keep the picture. All right. So let me just keep that down there for a second. All right. So here's the statement. So here's the theorem is Cauchy's formula. So we suppose that f is holomorphic on a domain D and gamma is a typical curve in D such that its interior omega is contained in D. Okay. Then if Z is in that interior, then f of Z is equal to this thing down here, 1 over 2 pi I, integral around gamma, f of zeta, over zeta minus z, d zeta. Why does it keep doing this to me? There we go. Okay, and this is shockingly easy to prove rigorously. You don't have to, not assuming any power series expansions, or don't have to justify any infinite integrals or anything, integrals of infinite sums or anything like that. Okay, so since z is an omega, and omega is open, we can choose a delta so small, so let delta be so small that the disk around z of radius delta, the closure of that is contained in D. Or sorry, in omega. Should be omega. Okay. So basically what we're going to do is take this, so we're just going to compute this integral around gamma here. And we can turn that into an integral around the boundary of that disk by the weak homotopy principle. And then the integral around the boundary of that disk, well, we'll see what we can do with that. So then, by the weak homotopy principle, for all rho less than or equal to delta. And so what I'm going to say here is, for any rho, so I can draw a smaller disk inside this disk of radius delta, and that is going to have radius rho. So that radius there, I'm crowding out my figure too much, but that radius there is going to be rho. Then by the weak homotopy principle, we can replace this integral around gamma with an integral around that disk of radius rho. Right, so we could replace it with the boundary of the disk of radius delta, but we could also replace it with the boundary of any potentially smaller disk as well. So the integral, so 1 over 2 pi I, integral around gamma, f of zeta over zeta minus z d zeta is equal to 1 over 2 pi I, integral around the boundary of this disk, the radius rho, f of zeta over zeta minus z d zeta. Okay, so well, what good is that? What good is that is that this holds for all rho, right? So this integral on the right-hand side has the same value no matter what rho I take. So what I can do is I can take the limit as rho goes to 0 there. So let's say, but the limit as that circle shrinks to nothing, 1 over 2 pi I, integral around that disk, well, we've done this integral before. We've actually done this limit before. Okay, so actually, for any continuous function f, you can say that this limit is equal to the value of the function at the center of the disk. So this is equal to f of z, because we've computed this before. So just for reference, this is by example 10 in 1.6. So you can take a look at that example. We've computed that limit once before already. So now we can finish the proof because here the integral over gamma, this is the integral over any one of these smaller disks of radius rho, right? And then we can take the limit. So as we move that rho smaller and smaller, the value of the integral over gamma is not changing. But that thing is limiting to f of z, so that tells us that f of z should be equal to this integral over gamma. So we'd have the following computation so 1 over 2 pi I integral over gamma f of zeta over zeta minus z d zeta. Well, that's just some number, so that's equal to the limit as rho goes to 0 of that same number. Right, and that's equal to the limit, and so now replacing integral over the disks and that limit's equal to f of z. All right. So that's Cauchy's formula for a holomorphic function. So any holomorphic function, you draw a typical curve that whose inside is contained in a region where the function is holomorphic, and the values of the function on that curve have to determine all of the other values inside of that curve. So that's kind of the takeaway from Cauchy's formula, just as kind of, so at a theoretical level, it's just kind of an amazing result. Okay. So one of the cool things about Cauchy's theorem, or Cauchy's formula, is that the motivation for where we got that formula from, we sort of supposed that there was a power series expansion in a small disk around a point, and that motivated where the formula came from. But it turns out that now that we've established the formula without any reference to power series whatsoever, it turns out we can use the formula to show that our holomorphic function has to have a power series expansion in a small, or at least around a small disk around a given point where the function is holomorphic. So here's the theorem that comes out of Cauchy's formula. It's one of the main theorems. So this is really, we're crossing multiple streams here. So we're bringing together the holomorphic stuff that we've talked about, like so derivative stuff, complex integrals, integrating around curves, and power series that we talked about recently. So these are all crossing all of the streams. Okay, so suppose that f of z is holomorphic in a domain D for any z naught in D. F has a power series representation or expansion in a disk around z naught. And from this, it follows that f is infinitely differentiable at every point in D. right? Because if it has a, right, the z0 was arbitrary. So we have power series expansion. We know we have derivatives of every order at every point in the disk where the power series is valid. And so we'd have to have infinitely many derivatives at any arbitrary point in our domain. So it suffices to figure out what this power series expansion is. Okay, so here's the proof. So let me draw us a picture here. So here's our domain. Maybe there's a hole in the domain, but we take a point z0 in the domain, and we can always find an open disk around that point that lies inside of our domain omega. So let's say that has radius delta. Okay, so I'll write this down. So our omega yes, omega is like this. Okay, so let proof. Let delta be so small that the closure of the disk of radius delta around z0 is contained in D. And let, just so we don't have to keep writing this, so gamma is going to be the boundary of that disk oriented counterclockwise. Okay, so if z is some point in the disk, and so z0, and then you got z in here, well, let's see. So at this z, well, we have the curve, you have the curve gamma going around there. And so by Cauchy's formula, f of z is 1 over 2 pi I integral f of zeta over zeta minus z integral over gamma, right? Because this gamma is a curve that's going around z. It's a typical curve going around z, and the interior of it is contained in omega by construction. Oh, I just realized. Yeah, I don't know why I've been calling this omega. I should be calling this d. Okay, sorry about that. That was confusing. Okay, so Cauchy's formula applies here, and we find that f of z is equal to this integral. Okay, so the plan, the idea, so remember I pointed out that this integrand is particularly simple in the argument z. It's this very simple rational function, right? So what we're going to try to use is the expansion 1 over 1 minus w. Basically try to use the geometric series. So 1 over 1 minus w, we know that's equal to 1 plus w squared plus dot dot dot. And this is valid when the norm of w is less than 1. Right, so we want to somehow use this, so find some natural variable w with norm less than 1 and apply this. So it's natural, so natural choice for w. The natural choice for w is, well, we're focused in this disk here, right? So we have the sort of vector that's emanating out from z0 to the curve, to the boundary circle, gamma, and we also have the vector that's emanating from z0 out to z. Right? And since z is inside this, strictly inside this disk, the quotient z minus z0 over, say, zeta minus z0, where zeta is on the boundary curve there, that's going to be less than 1 in norm. So the natural choice for w is the following. It's z minus z0 over zeta minus z0, where zeta is on the curve gamma. Okay, so that's basically going to be the game plan. And how that works is like this. So we take f of z, and just copying down what we already have. And I want to get z0 involved here, right? So typical way to do that. And I'm keeping my eye on, I want to use this 1 over 1 minus w expansion, so I don't want to mess with this too badly. And so the idea I land on is to insert z0 in the denominator like this. Right, just algebraically that's the same, so nothing wrong with that. And then to get to this guy here, we just do what? We're going to pull zeta minus z0 out of this denominator. Okay, so again, just purely algebraic move. What we're going to have is, we got the numerator, I'm going to pull that zeta minus z0 out. Okay, pair that up with the f of zeta, and what we have left is 1 minus z0 over zeta minus z0. And then we're doing that, integrating that d zeta over gamma. And as I said above, this z minus z0 over zeta minus z0 has has norm less than 1, so it has a valid, so we know that the geometric series is valid for that particular value. So what we can say is that this is equal to 1 over 2 pi I integral over gamma of f of zeta over zeta minus z0 times the sum, n equals 0 to infinity, of z minus z0 over zeta minus z0 to the n, and then d zeta. Okay, so we know that that's valid. Computation is valid. Okay, so the basic thing we'd want to do to finish the computation is we'd like to interchange this sum and integral. So assuming we can interchange the sum and integral, we have that f of z is equal to, let's see, so if we can pull this sum out, we would have the sum from n equals 0 to infinity of 1 over 2 pi I integral over gamma f of zeta over, so we got the zeta minus z naught, the 1 power, but then we also have n powers of it. So we have n minus 1, or n plus 1 powers total, zeta minus z naught to the n plus 1, d zeta and then z minus z naught to the n. And this right here, that's our an in our power series. Okay, so we're done, assuming that we could naively do that interchange of sum and integral, but this infinite sum, that's a limit inside this integral. The integral is another limit, and so interchanging them is interchanging these two limit processes, and it's not really clear that's valid. So how we can proceed? So to proceed, so basically, if we could interchange this infinite sum and an integral, we'd be done. But what we know is that we can say that the integral of a finite sum is the finite sum of the integrals, right? Everybody knows that. So we use that fact. So we use the fact that we can interchange integration and finite summation. Okay, so let's go back to where we were. We had f of z was equal to 1 over 2 pi I times the integral over gamma of f of zeta over zeta minus z naught, sum from n equals 0 to infinity of z minus z naught over zeta minus z naught to the n d zeta. Okay. And what we want to do, so I don't think I need the stuff above there. All right, don't want to run out of room here. Now, so what we can do is we're going to break off the first capital N terms in this sum. Right? So just consider the first n terms. So that's a finite sum. So we'll be able to interchange the integration and the summation of those first n terms, capital N terms. So that's what I'm going to write here. So this is 1 over 2 pi I, and the integral over gamma of, so we have the sum from little n equals 0 to capital N of f of zeta over zeta minus z naught to the n plus 1 times z minus z naught to the n plus the rest of them from little n equals big N plus 1 to infinity of f of zeta over zeta minus z naught to the n plus 1 c minus z naught to the n. And we're integrating that all d theta. Okay, so as I said, we are going to interchange the sum and the integral in the first summand here, because we can do that because that's finite. So what we find is we have the sum from n equals 0 to capital N of 1 over 2 pi I integral over gamma f of zeta over zeta minus z naught to the n plus 1 d zeta times z minus z naught to the n. And then we have the other term, so that's plus 1 over 2 pi I integral over gamma Okay, so now basically what I claim is that this first term in blue here, as n goes to infinity, that's the same as this expression up here, right? As that capital N goes to infinity, right? So this is as capital N goes to infinity, right? That approaches that, and that's what we want to say that our f of z is, right? So what we know is that right now, so we've got to be careful. This one up top, this line up top, this is what we want, right? And what we've actually established is down below. F of z is this finite sum, the first capital N terms plus this other stuff. But that first finite sum, as we take the limit as capital N goes to infinity, it approaches the thing we want f to be equal to. Right? So all we have to do is show that this term here, we basically want to show that this goes to 0. So we want to show this goes to 0 as capital N goes to infinity. Because if that went to 0 as capital N goes to infinity, then that would mean that this first summand in the blue box, that's approaching f of z. And so we actually have the expression of f as a power series, as we claimed. Right, so we'll be done if we can show that that thing in the yellow box goes to 0. Okay, so here we go. Proof that yellow box goes to 0. Well, it goes to 0 as capital N goes to infinity. Okay, well, we'll just look at the absolute value of it. We'll just see that the norm is going to 0. So the absolute value of 1 over 2 pi I, and we're just going to estimate it from above. So we'll show that it's bounded above by something that's going to 0. Little n equals n plus 1 to infinity, f of zeta minus z naught, to the n plus 1, c minus z naught to the n, and d zeta. Okay. It's less than or equal to, so the norm of 1 over 2 pi I is 1 over 2 pi, right? And then the integral the absolute value of this integral is less than or equal to the length of the curve. So that's the length of gamma. And remember, gamma is a circle of radius delta, right? So that's 2 pi delta. So this is the ML inequality, max length inequality. Okay, and then the max over gamma of the function inside, which is this whole big mess. Okay, so we have to estimate that. Well, so we have absolute value of, the inside is really this limit, right? But absolute value of a limit is the limit of the absolute value. And then, so we can pull that limit outside. Then we just have a finite sum, absolute value of that. And the absolute value of a finite sum is less than or equal to the finite sum of the absolute values. So, and then once you put the limit back in, what we essentially find here is that this is less than or equal to, so we have delta, and we have the sum, n equals big N plus 1 to infinity of the, excuse me, be careful here. Delta, and then the max over gamma of all of this stuff. So we have the sum of f of zeta, norm of that. Yeah, so norm of this over zeta minus z naught to the n plus 1 times the norm of z minus z naught to the n. Okay. Well, let's see. So this is less than or equal to, so the norm, so right here in this denominator, zeta minus z naught, that's on gamma, and that has length delta, right? So let's see, yeah, so we can say that, so that has length delta. So delta times the max over gamma, the sum, n equals n plus 1 to infinity of absolute value f of zeta over, we have delta to the n plus 1, and then we have norm z minus z naught to the n, right? And let's see here, so our so now basically we'll take this, we'll cancel this delta here with this 1 here, right? And then what we have is the max over gamma of this sum. Yeah, and so the max over gamma of f of zeta. Right, so you can just pull that out of the sum because that doesn't depend on n. And then we just have sum n equals capital N plus 1 to infinity of norm z minus z naught over delta. And that's to the n. Okay. All right. And the zetas, which are on gamma, that's only in this term here, right? So this max, this is just the sum is just a constant as far as the variable zeta on gamma is concerned. So we can just cordon off that max in the front there. And let me just call this m. Okay, so this equals m times, well, let's see, this series here, this is a geometric series, right? And it starts with the term, this thing in the parentheses to the n plus 1. So what we got is norm z minus z naught over delta to the n plus capital N plus 1, and then we just have a geometric series. And we know the sum of a geometric series. It's 1 over 1 minus the ratio, and that's norm z minus z naught over delta. And that's valid because norm z minus z naught, z's in the disk of radius delta, so this ratio is strictly less than 1. Okay. And so we note our dependence on n here. I mean, this here, this is just a number. This is just a number. And then we have this ratio here. So that's less than 1. And we're raising that to the n plus 1 power. So since that's less than 1, that's going to go to 0 as n goes to infinity, big N. Okay. And so that establishes that the yellow box, that goes to 0. And so indeed, this blue, which is approaching this infinite sum here, this power series, that does approach f of z. So we get convergence inside this disk of radius delta, and that completes the proof. Okay. Cool. All right. And now, so what we can note, so let's write that out clearly. So if we have a domain D, so f of z is a holomorphic in D, and z naught is in D, then we have f of z is equal to sum, I guess I should say z naught in D, then near z naught, so in a sufficiently small disk. And then near z naught, we have that f of z is a power series. And that power series, the coefficients of it that we computed in the proof is the following. It's 1 over 2 pi I integral around, so you have a little disk. So let me, maybe I should make that clear. So we have around the boundary of a small disk, so disk around z naught of small radius delta of f of zeta over zeta, right, yeah, zeta minus z naught to the n plus 1 d zeta, and then so this is our an, so the n comes in the power of zeta minus z naught in the denominator there, times z minus z naught to the n. Right. But we saw at the end of last class, so in general, if f of z is equal to a power series like this, then the ANs must be equal to the nth derivative of f at z naught divided by n factorial. Okay, so if we compare this to the above, this means that the nth derivative evaluated at z naught over n factorial, that must be equal to the integral over this disk of f zeta over zeta minus z naught to the n plus 1 d zeta. Right. Okay, so what we find is this is actually a generalization of Cauchy's theorem, or we can wring a generalization of Cauchy's theorems out of this, because the n equals 0 case, right, is exactly basically Cauchy's theorem, just for the using the boundary of a disk as a curve. So we can insert a more general curve in here. So a corollary of this power series expansion result is Cauchy's formula for derivatives so if we suppose, so basically this is just the same setup as in the original version of Cauchy's theorem. So suppose f is holomorphic on a domain D, and gamma is typical in D such that its interior omega is contained in D. If z naught is a point in that omega, then the nth derivative of f at z naught over n factorial is equal to 1 over 2 pi I integral over gamma f of zeta over zeta minus z naught to the n plus 1 d zeta. Okay, and the proof is just the discussion above. And the weak homotopy principle. And so the integral over this gamma is going to be equal to the integral over the boundary of that little disk. So you can, so inside this gamma, so gamma bounds omega, and in that omega you got z naught. You can put a little disk around z naught, and then the integral around gamma is going to equal the integral around that little boundary circle of that disk. And so this integral around gamma is going to be equal to that derivative. Okay. Right. So just as the value of your function is completely determined by the values of, so the value of the function at any point inside omega is determined by the values of the function just on the boundary of that omega. Actually, all of the derivatives, so all the derivatives of any order at any point in omega is completely determined by the values of the function on the boundary curve omega, or sorry, the boundary of omega, which is gamma. Right, you see in this integral, there's no, the only information in this integral is just the values of the function on the curve itself. That's the only place the function is coming in there. So it's purely the values of f on that boundary, which give rise to the values of the derivative at any point inside in the interior of gamma. All right, and that's pretty much perfect timing. So I'll just say thanks for being patient, working with this new technology. And I'll see you guys soon.